Not even sure what that is exactly. But we start off here with a proof. And I know I said proof went away, but we're just basically proving the first theorem here. And so in this theorem here, we're basically given perpendicular. We have to draw in some radii, which makes sense. Radii are congruent to each other. And of course, you got a reflexive side right down the middle. That gives us, by CP/CTC, after the congruent triangles, those two sides are congruent, which tells us that OP bisects AB. Now what that tells us is that if I have a radius right here drawn perpendicular to a chord, this is a chord, then that radius is going to bisect the chord. So if a radius is drawn perpendicular to a chord, then it will bisect the chord. And like many of our theorems, it's reversible, so it goes in both directions. So if a radius bisects a chord, it is also perpendicular to the chord. And then one more related theorem to that, before we get into some definitions and then looking at some problems, is that if there's a perpendicular bisector of a chord, then it goes through center of a circle. Okay, so that's the theorems for this section. And there's some definitions here. I've already mentioned a few things, but let's just make sure, we'll backtrack here and make sure that everyone's on the same page. So a circle we've talked about in one of the very first chapters of our book. And a circle is the locus of points that's equidistant from a given point. And I should mention that here it needs to say in a plane. Because if we don't mention that it's in a plane and we think about it, it can be in 3 dimensions, then it becomes a sphere. So that is an example of a circle. Here's the center. Here's the radius. I think everyone knew that. An arc is basically, if I have 2 points on the circle, then this right here, joining those 2 points on the circle, is an arc of a circle. Concentric circles are circles that share the same center. Interior points, exterior points, I don't think that's any real big deal there. A chord basically is a line segment joining 2 points that are on the circle. A special type of line of chord is, of course, a diameter, and that one is basically a chord that goes through the center of a circle. The distance from the center of a circle to the chord is going to be the perpendicular distance. So we're talking about the perpendicular distance. And a sector is basically going to be like a piece of the pie. That's going to be a sector. We'll get into more of that later in the chapter. Area of a circle, of course, is going to be pi r squared. Most of you should know that from elementary school. And the circumference of a circle is pi d, also known as 2 pi r, where d is the diameter and that is the radius. Okay, let's jump over to the second side here and let's talk about, or let's try some of the problems. So problem number 1 here says approximate the length of the chord rounded to the nearest hundredth. That's because we're going to use trig here. If the circumference of the circle is 24 pi, so circumference is equal to 24 pi. And we know that the formula for circumference is going to be 2 pi r. And so we can see from this equation right here that we can solve for the r. The r is going to be equal to 12 in this case. So we know that this is 12. And we also know that this angle right here is 106. So if I go ahead and split this right here and draw a radius perpendicular to the chord, this of course will split this angle in half here. This will be 53 degrees. And I can do some trigonometry using sine. So sine of 53 is equal to, let's call this side x over 12. Plug that in my calculator. X is equal to whatever 12 sine 53 is. Double that and you'll get, I think, what is it, 19.17 here. I'm looking at my cheat sheet over on the side here. The second problem is a problem that is pretty common in this section. You're going to have a circle with a diameter of 40, something like this, which tells you that the radius is equal to 20. And you want to find the distance from the center to a chord that has a length of 24. So this chord right here has a length of 24. Need to draw the radius perpendicular to that, which is going to, from the theorem on the front side, it's going to split that chord in half, so that's 12. I already know what my radius is, so I'm going to draw in the triangle. This is super common here where you have to kind of form these right triangles like this. This is going to be 20, and then I can do, it's a triple, so this is 16, and that'll be the distance from the center to the chord. Next problem here is a circle with an area of 900 pi. It's equal to pi r squared. The nice thing is the pi's drop out of that. R is going to end up being 30. So a lot of these problems, you have to figure out what the r is first. So then I'm going to go ahead and draw my diagram in here. The chord has a length of 48. And I know I need to kind of draw in the same type of diagram like this again. So I know that this is going to be 24 because this radius drawn perpendicular to the chord is going to split that chord in half. The radius we know is going to be 30 right here. And I can find that distance. What are we looking for here? We're actually looking for the measure of the central angle, which is defined as the angle with the vertex at the center. So determined by this chord right here. So we actually need to know this angle right here is what we're looking for. So I can find this angle here. This, we'll call it theta. And so I know this side and I know the hypotenuse. So it's going to be the sine again. So sine of theta is equal to 24, the opposite side, over the hypotenuse. Inverse sine both sides, you get theta is equal to 53.08, and then just double that. You get 106.16, and that's going to be your angle measure, the central angle. And then this is the last problem I'm going to do here. And this is always a problem that I would have the class work on, and it would take about 15 minutes or so to work on. If you want, you can go ahead and stop the video and try it on your own. But I'm going to go ahead and just go through this right now. This is 15. This radius is 13, excuse me. And the distance from center to center is going to be 14 right there. And so when I'm approaching this problem, I'm trying to find the length of the common chord. The common chord right here is going to be this length. Kind of highlight it right here. It's going to be this is the chord that's in common between the two circles. That's why it's called the common chord. So what I'm going to go ahead and do here is I'm going to make x equal to this little segment right here. And because that's equal to x, I'm going to go ahead and call this little piece y right here, which will be half of the orange segment. If this is x, and I know that this is 13, I know that this must be equal to 1 because, remember, the entire length from center to center is 14. And so from this triangle, I just focus on this triangle right here, this right triangle, I can go ahead and do a little equation here. Y squared plus the whole length on the bottom here is going to be x plus 1 squared, and that's going to be equal to 15 squared. That's one equation using the Pythagorean theorem. Second one is going to come from, let's use a different color here. Let's use the something like this. Okay, that's going to be that right triangle right there. And so that one, if this is x, then, and I know that this whole thing is a radius from this point over to this point is a radius of 13, then this side right here is going to be 13 minus x. So I can do y squared plus 13 minus x squared is equal to 13 squared. And then I have a system of equations and I can solve that thing. Might want to solve both equations for y squared and then, you know, set these two parts equal to each other. When I solve that system, x is going to be equal to 8 and y is going to be equal to 12. And then when I plug stuff back in, you're going to end up with a chord of length 24, since the chord is just double my y value. I will mention also that you can also do this using the law of cosine, because I know this side, and I know this side's 13, I know this side's 14. If I focus on this triangle, I can find one of these base angles down here, like this angle right here, let's call it theta. And then once I find theta, I can use regular triangle trig with this yellow right triangle there to solve for this side right here and just double that. I'm going to stop right here. There's two more problems here which I'll give you the answer to if you want to try them. I know that the answer to number 5 is, this ends up being equal to 2. And then this one, ST ends up, this is another one that's going to be a time-consuming problem, but it's a great 4-level problem. It ends up being 2.71. So give those a shot if you want. There's some great problems there. And yeah, give it a shot. All right, that's it. Thanks for your time.